Okay. Maybe we could get started now.
Mm.
Today we're honored to have Juno Nam from MIT. Juno is a third year PhD in MIT, and he's going to talk about his research, his work during his intern at Meta Fair Chemistry.
Okay. Thank you for introduction, Tony, and yeah, I'll start my presentation. Um, can everyone see my screen?
Yep.
Yep, thanks. Okay. So I'm Juno, and I'm a third-year PhD student in MIT Department of Material Science and Engineering. So I'm more from like chemistry or material science background. And today I'll be talking about enhancing diffusion-based sampling with molecular collective variables. And as introduced, this is the work that I did when I was interning in their chemistry team at Meta. So uh, the TLDR is like this. So we usually have a diffusion-based sampler that is trained based on the energy function alone. But now we're gonna add adaptive bias to like during the sampler training to smoothen out the landscape to prevent mode collapse and also reproduce the free energy landscape from the constructed bias. So I'll start from explaining why do we need sampling in chemistry. So informally, we want these kind of applications. So given the energy function and the system and thermodynamic conditions like temperature, pressure, like etc., we want to sample possible configurations. So for example, if we say our system is 6 water molecules, then we want to sample like different configurations of 6 water molecules that are organized in space. And another example is if we have a lithium phosphate, then we want to sample different like polymorphs, so different arrangement of atoms that are arranged in periodic space. And also we want to know like which of these configurations are more favorable in the given thermodynamic conditions. So this is formalized as sampling from Boltzmann distribution. So ideally, we want to generate samples from the distribution that is given by the exponential of the negative energy function, where the negative energy function, the reduced energy function encodes the given information from the energy, like base energy function, and also the system and thermodynamic variables. Usually, we start from canonical ensemble, where we are given the number of particles and given the volume and temperature, in which case our Boltzmann distribution, the reduced energy for the Boltzmann distribution becomes minus beta times E, where beta is the inverse temperature parameter. So there are two main ingredients if we want to learn the sampling distribution. And we can either learn from the data that are already sampled by existing samplers, or we could also learn from energy function without relying on the existing data. So definitely learning from energy is more exciting because it is also costly to generate the data because classical samplers like molecular dynamics or MCMC has slow mixing times. So we have to wait for a long time. But also, learning from energy is more challenging because of the reasons that I will explain later. Historically, this line of like learning the sampler started from the seminal work of Boltzmann generators, which developed normalizing flows that converts the prior to the data distribution and could be learned either from data by using maximum likelihood or from learn from energy function by using reverse scale divergence. And since then, there have been two major paradigms of developing these kind of Boltzmann generators. The first one extends the normalizing flows, and they try to make normalizing flows more capable of learning complicated distributions by developing scalable architectures and training schemes. And the second paradigms rely on diffusion samplers, which is basically we train a diffusion model based on the feedback from the energy function that we have. So the basic motivation for diffusion sampler is we're given the base generated process that has like base drift and diffusion term. And now we want to control this process by adding a control term, which is learnable. And we want to control this diffusion model towards the reward tilted distribution. That is the base distribution density multiplied by the exponential of the reward function. And usually this reward function can be something like for image generation models, it could be the quality oracle. And for specifically for the case when we want to sample from an energy function, then we essentially want to tilt the diffusion process with the reward that is given by the negative energy function and the base density term, so that our reward tilted distribution becomes the Boltzmann distribution that is given by the energy function. So there has been multiple ways, like various ways of training the diffusion samplers from the energy function. But the method I'll introduce today is based on the approach called adjoint sampling. So adjoint sampling is informally similar to score matching, but instead of getting supervised by the difference between the prior sample and the data sample, we are now supervising our intermediate control by the gradient of the tensile energy at the final data point. So essentially, the matching objective looks like this. So first, we use the current control model to and integrate the diffusion process to get the final samples x1. And now we add noise to the final sample to get intermediate data points. And at that intermediate data point, we will regress the control model against some form of transformed energy gradient that is based on the reward function that we had before. So the energy function, and also it includes the base density at the final time. So essentially, we're regressing the intermediate control against something that we can obtain from the final time step. So this is quite efficient because this kind of reciprocal projection enables us to, at some point, generate a bunch of like final data points and save this regression target. And after that, we save that into the replay buffer, and we sample intermediate time step from the replay buffer and just regress it against the final that regression objective. So this kind of training scheme is very efficient for diffusion samplers and has been extended to like a range of different other objectives. But in the current form, when we derive this reciprocal adjoint matching objective, it requires that the diffusion process is memoryless, which basically means that our prior distribution and our final data distribution has to be independent, which is quite a restrictive objective, because when we start from like a delta prior to make it memoryless, then initially at the very initial time steps, every sample would look alike, but we have to diverge them into different modes of the data. So it's more challenging to learn in the initial time steps. Nevertheless, like the joint sampling method has been applied to some chemistry applications where we essentially condition the control model based on the graph 2D graph of the molecule. And uh, we learned this sampler across like different molecules to, and just by using the energy function. And by doing so, we obtain an amortized conformer generator that is trained just by energy and on some like training smiles data set, and that could be inferred on like different set of smiles strings. So yeah, basically we get a conformer generator that is learned by energy function. So after this, a joint sampling method has been extended to non-memoryless condition by the method named adjoint Schrödinger bridge sampler, which uses the Schrödinger bridge formalism and connects it to the SOC formalism to enable the use of an arbitrary prior distribution instead of the delta one. So the idea is we have additional term at the regression target named corrector, which corrects the effect of a non-degenerate prior that we have. And this corrector is also learned from the gradient of the transition-based density, so that we can iterate between the joint matching and corrector matching objectives to iteratively refine this corrector to correctly delete the effect of non-degenerate prior and also enable this adjoint matching to guide this control function, like control mole, to eventually tilt the base diffusion process to sample from the Boltzmann density given from the energy function. So it has been shown the like total performance on synthetic energy functions like Leonard-Jones particles and the Gaussian mixtures. There's like one apparent limitation of ASBS and for the other IID diffusion samplers. So for example, if we try to sample alanine dipeptide, which is like a simplest molecule benchmark, then there in the ground truth, when we project the sample configurations onto two torsional angles, phi and psi, then there are like usually two major modes. So like the one more populated one on the left and less populated one on the right. But when we use ASBS to sample from uh, to learn from the energy function to generate alanine dipeptide samples, then usually mode collapses and generates only the samples from the major mode. And this kind of mode-seeking behavior is somewhat of a fundamental limitation of this method, because when we learn from the energy function, essentially we're learning from the energy feedback from the sample that we generated. So say we have like two different modes, and at some point, if we only generate samples on the mode on the right, then essentially the feedback from the energy function will guide us downwards to on the potential energy landscape. So we have to be very lucky to overcome this energy barrier and also explore other modes. So this kind of like self-reinforcing behavior is kind of inevitable if we just want to learn from energy function. So this is kind of main limitation of current sampler that motivates the current work of enhancing diffusion-based samplers. So for alanine dipeptide, it could be, it might look simple, so that if we train it using some kind of regularization, then it might get like less populated mode as well. But for different type of sampling approach, like for more complicated type of sampling in chemistry, we can actually have more intense mode collapse behavior as well. For example, this is one example that I tried. Is Leonard-Jones particles, but instead of like having them in a vacuum, we have a periodic boundary condition that confines this Leonard-Jones particle in a box. So this is like a minimal mole for like solid or liquid system that we have in material science. And For liquid system, we can see that like if we try to learn a sampler for this distribution, then we get a good overlap between reference and generated distribution, which is because for liquids, particles can move around pretty fast, which means that the modes are smooth. So they have sufficient overlap for the diffusion process noise to guide us to a different mode as well. But for solid systems, usually uh, the Boltzmann distribution in solid system is very confined in the very narrow crystalline minima. So in order to get into this very narrow minima just from the random noise, then we have to be extremely lucky. And if not, then our diffusion process will initially guide us towards somewhere in this glassy landscape where like there's a very like plenty of tiny microstates that are local energy minimas. So like this kind of behavior makes us to seek some kind of enhancing enhancing the sampler to prevent mode collapse so that we can find the modes that we want. And another problem that we have is the sampling efficiency. Let's assume that like there are two different metastable regions in the energy landscape that differs in free energy by delta F. Then if we train an IID Boltzmann generator, then if the model is ideally trained, then it'll produce 1 to the exponential of minus beta times this free energy difference uh, in like sample ratio in the less and more populated regions. And when we think of like practical example, when we want to sample like protein ligand system that has a nanomolar binding affinity, which correspond to uh, a ratio of 10 to the ninth. So it's pretty extreme. So that the observables that depend on getting samples from less populated regions could suffer from prohibitive statistical uncertainty. But for chemistry applications, we kind of want to reproduce those like physical observables that also relies on the less populated regions. And the main cause of this is because of the gap between what we can simulate and what happens in reality. So the importance of less populated regions, even if it's really less populated, it could be important because chemical processes happen in real time where like there's almost like infinite number of microscopic events happening in chemical processes in real time. So like the physical processes can explore the full thermodynamic ensembles, including the much less populated regions. But there's our simulations are bound by the time steps that we can take during simulation. For example, when we run molecular dynamic simulations, usually what we can afford is up to like a few microseconds of simulation. And those kind of correlated samplers will generate vastly fewer samples than what the real life physical sampler is producing. So essentially this gap have to be filled by non-IID sampling, which also motivates for enhancing the diffusion sampler, like some kind of enhancing algorithm that augments the diffusion samplers. So finally, before introducing the algorithm, I also want to introduce one more like practical requirement for sampling. When we think of Boltzmann distribution, it's the distribution that's given by the exponential of minus beta times energy function. But it's usually very rare that we want to sample the entirety of that Boltzmann energy landscape. For example, we can think of like small amino acids. It is known that like there are two uh, like enantiomers, which is the mirror symmetric configurations of this amino acid. So there's L configuration and also there's D configuration. And they are actually chem like chemically they're the same uh molecule, but they have a different configuration. And if we think of like interconversion between these two molecular configurations, then like other types of molecular configuration changes, like the rotation of torsional angle or like conformational changes happens in relatively short amount of time. Like it happens in real time. But interconversion between like L and D amino acids are like they have very significantly higher energy barrier. So it almost never happens in real life. And almost all amino acids that we encounter in real life is L amino acid. So that means we have to aim at some kind of kinetically connected component from a single reference configuration that we have at certain timescales. So basically, we don't want to sample the entirety of Boltzmann distribution, but we want to sample some connected component that starts from an initial like configuration. And the second one is related to the previous limitation. So instead of doing IID sampling, we want to generate a pair of like sample and weight pairs so that we can use a self-normalized estimator as shown below here, which we assign different like samples with different weights so that we, as we get like many samples and weights, we reconstruct the Boltzmann, like the physical observables from Boltzmann ensemble. So now, since we have laid out the practical requirements for the Boltzmann sampling that we want in chemistry, we will discuss how to realize this via employing inner sampling mechanisms in diffusion samplers. So this is a translated version of previous requirement into like a formal setting. So first, we want a restricted support. So we have some kind of connected component or accessible component A that we want to confine the sampling on. And we can do that by using a restraint potential that are essentially zero on this A, like accessible component, while we kind of strongly penalize all the configurations that are outside A. For example, when we want to confine the sampling to L amino acid instead of D amino acid, then the the order parameter that discriminate between these two states are the improper torsion angle centered at this carbon. So we can use some kind of harmonic potential that is zero when like some kind of flat bottom harmonic potential that is zero when we're in L amino acid, but that kind of goes up when we get into the amino acid range. The second and third requirement is that we want to do weighted sampling, but this kind of weighted sampling scheme should converge to the correct Boltzmann ensemble. And also, we want to sample efficiently, which means when like the free energy difference between two modes are really large, we don't want to sample that in like IID sense, but we want to do weighted sampling that we can get sufficient samples in different modes, even if the modes have different population. And for this, we will use some kind of biasing scheme that will be introduced later. So we will essentially, the intuition here is to selectively increase the sampling temperature along some like selected low dimensional descriptors. So if we have like, so basically we add some kind of bias potential And we train a sampler on the energy function, the base energy function plus this bias energy, so that we kind of smoothen out the energy landscape to get the samples from like wide regions of configuration of space. And then we reweight the samples with this additional bias to correct the sample weights to reconstruct the Boltzmann ensemble. So to do this, we apply in-end sampling approach. And there are like various flavors of in-end sampling approach that facilitates the sampling of rare events, like the sampling of events that crosses the energy barrier by biasing the simulation toward uh, the regions that we are interested in. And in order to do so, there are like different approaches that either uses collective variables or just using like different ensembles, like multi-thermal or like replica exchange. But here we will introduce the collective variables approach, which is essentially the low-dimensional descriptor of slow or like important motions of the system. So for like example, if we have alanine dipeptide or like different peptide systems, then we know that the backbone torsion angles, phi and psi angles, are the slow degrees of freedom that we want to enhance the sampling on. And another example is the host gas system, like the protein ligand system, that we have a host molecule and a small guest molecule that is bound to it. And in this case, we can use some kind of distance between the center of mass of the host and the guest molecule as this kind of descriptor. And as soon as we get that kind of collective variables, we can enhance the sampling by different approaches. So the well-known and the oldest algorithm is umbrella sampling, where we apply umbrella potential along this collective variable space to confine the sampling. And then finally, we reconstruct the entire landscape by some form of like M-bar like reweighting scheme. And another one is metadynamics, which we will use later. So in metadynamics, we slowly fill up the potential energy landscape so that when we start to fill up the potential energy landscape, at some point, the molecule or particle will overcome the barrier and start exploring other regions as well. And another like well-known flavor of in-end sampling, like collective variable-based in-end sampling, is adaptive biasing force, which is we keep track of the force at some collective variable point that is experienced by molecule. And we bias the simulation towards the negative direction of that force. So effectively, this is kind of shaving off the energy barrier to overcome this barrier. So while metadynamics is kind of stacking up the potential energy landscape, adaptive biasing force is shaving off the barrier. So they're kind of complementary, and there are even like methods that combine these two approaches as well. Yeah, and in this work, we'll start from the variant of metadynamics called well-tempered metadynamics that is known to have a good convergence behavior. So essentially what we do here is originally coupled with molecular dynamics simulation. And we run molecular dynamics simulation. We start from the same setting, but every like couple MD steps usually is taken like 500 MD steps. We update a bias on the collective variable space. So we stack a Gaussian on the collective variable space centered at the current collective variable sample. And when we keep doing this for during the MD simulation, then essentially we will stack up the bias and flatten out the potential energy landscape. And another important component here is we don't stack up the same Gaussian kernel at every time step, but if there's some amount of bias potential that is already constructed, then we have some kind of discount factor that slows down the addition of bias. And according to this factor, the gamma factor that is used to use as a discount factor, the final bias will converge to some smoothened version of the original potential energy landscape. And uh, yeah, this bias corresponds to some scaled version of PMF, which is potential energy, like potential of mean force, or alternatively, we also call it as free energy landscape, essentially, which is the negative log marginal density over the low dimensional collective variables. And obtaining this kind of PMF is usually one of the main goals in chemistry sampling, because when we project the like marginal density as the some kind of free energy landscape, then we can locate where is the free energy minima and also know like how much is the free energy barrier between two metastable states. So this means that like we will essentially smoothen out the free energy landscape by applying the bias, but also after like running this well-tempered metadynamic simulation, we can reconstruct this PMF from the final bias by applying the scale factor. And the final point I mentioned is that this bias, and so essentially after convergence, this bias adds up to the original potential energy landscape, and it's the final MD simulation will behave like so for the like in the collective variable space, this additional bias will behave like as if we are sampling from. So if our original MD simulation was running at temperature T, then with application of this bias, it will correspond to sampling from gamma times T temperature in the collective variable space, while retaining the original temperature in all other orthogonal directions from collective variables. So this is what we mean by selective increase in the sampling temperature along the like collective variable space. So since we have introduced well-tempered metadynamics, we will now combine this into the diffusion sampler ASBS and construct well-tempered ASBS. So what we do here is we keep the inner loop of the ASBS training, which is essentially for fixed current bias, we train diffusion sampler with energy function that is given by the base energy plus the bias potential. And we do this until this diffusion sampler converges and sample from this energy function. And the outer loop is we use this train sampler to produce IID samples from the current energy plus bias landscape and get the collective variable data points. And at every collective variable data point, we will stack the Gaussian bias with well-tempered discount factor. So yeah, essentially, we're drawing an IID samples and stacking up the bias as we do in well-tempered metadynamics. So an interesting viewpoint of this is when we start from like when our energy landscape is multimole and there's some energy barrier that hinders like correlated samplers like MD from sampling the entire landscape, then it's usually easy to get samples from one mode. And it's also easy to train the diffusion sampler that is trained by data of the single mode. So up to this point is an easy starting point. But if we only train by energy, then we'll get the same self-reinforcing behavior that essentially confines the sampling in this mode. But as soon as we turn on this outer step of well-tempered bias update, then we'll start stacking the bias potential on this mode of the energy landscape. And the sampling distribution will slowly tilt to another mode as well. And after running this until convergence, then we can probably get the same convergence behavior of binary bias that smoothing out the landscape. And we can also do the same kind of reweighting to get the free energy landscape from the constructed bias and from the weight back, like the reweighting factor and the samples from this ASPX model, we can reconstruct the Boltzmann ensemble as well. So this is how the combination of diffusion sampler ASPS and well-tempered bias addition mechanism looks like. And when we compare to the metadynamic simulation, by combining this biasing mechanism with diffusion sampler, we can move, like the diffusion sampler will generate uncorrelated samples from the current sampling distribution. So instead of like running MD and generating time correlated frames, we can move in all different directions in potential energy landscape. So it will show advantage in having efficient and parallel exploration directions where there like are many modes in the system and barriers are high. While there are a few disadvantages where diffusion samplers require restraint potential, as I mentioned previously, because in molecular dynamics simulation, proposal of the next step is respect the physics of the system that we have. So things like chirality inversion in amino acid never happens in MD, but diffusion samplers kind of samples by adding noise. So this kind of inversion can happen if we don't apply restraint potential. So this means that for well-tempered ASPS, we have to be careful with setting up the restraint potential. And another one is that there is an additional cost that is incurred by integrating the stochastic differential equation. And it involves like using the neural network control model that we trained. And also it's usually a few hundred NFVs. So if we combine this with classical force field, then there are actually not much gain from combining well-tempered mechanism with diffusion samplers compared to just leveraging classic MD or MCMC methods. But we'll see like in which case well-tempered ASPS can be actually beneficial even in terms of walk-log time. So we'll start from a very classical example of alanine dipeptides where we have two collective variables of two backbone torsion angles, phi and psi. And as previously mentioned, we start from pre-training from data where we can easily obtain the samples from like major like samples from the more populated mode by a very short MD simulation. And then we start the well-tempered ASPS loop where we keep adding the bias potential on the collective variable space on locations that we generate sample. And after like a few training steps, we will get samples from the less populated regions as well. And we will also get bias added to that region. And the loop will slowly converge to the final bias from which we can reconstruct the free energy landscape, which which agrees pretty well with the reference PMF that we have from extremely long MD simulation. And in this case, we can also look at the free energy convergence between the more populated mode versus less populated mode. And we can see that we can get a free energy convergence reasonably fast, even compared to the well-tempered metadynamics. So the benefit here is we get the free energy convergence and also prevent mode collapse as well. But the thing is, the x-axis here is the number of energy evaluations. So we're ignoring the number of function evaluations with neural network, the control mode that we have here. But nevertheless, we will move on to the tetrapeptide case, where in this case, we have 8 separate modes when we look at the three-dimensional space spanned by 3 backbone torsional angles. And we'll also use these 3 torsional angles as collective variables. And in this case, if we measure like the number of states that are explored up to a certain number of energy evaluations, then unbiased methods like just running plain MD or training ASPS, the diffusion sampler, starting from this mode, uh, is usually very slow at exploring states. But as soon as we turn on the biasing mechanism, then we can see that well-tempered metadynamics and well-tempered ASPS both explores states pretty quickly. And we get extra advantage by combining this with diffusion sampler, because when our well-tempered biasing mechanism is combined with MD, then it has to explore states one by one because it's time correlate, like it's generating time correlated frames. But well-tempered ASPS can explore different directions at once because it generates IID samples during training. So we can get advantage of fast state exploration. But in this case, we have slower free energy convergence because getting the free energy correct also depends on sampling different regions inside mode correctly. So in this case, if we combine with molecular dynamics, then it'll definitely have more advantage in terms of like sampling the conformational distribution inside the mode. So you can see that there's a trade-off between exploration and convergence speed. And then like these 2 examples are using the classical force fields, the Amber force fields. But as we previously explored, when we combine with classical force fields, then just running MD is usually much faster. But we have some examples like reactive energy landscape, where the system features bond breaking and formation, which couldn't be described by classical force fields. And the like the very basic approach of doing this sampling is combining the sampling algorithm with the quantum mechanical calculation. So there are methods like ab initio molecular dynamics where we perform quantum calculation at every MD step, but which is very slow. So people have been developing machine learning intraatomic potentials, which is essentially a regression model that is trained by like a lot of energies and forces label from the quantum calculation. And as we train this surrogate model of quantum calculation, we can get order of magnitude faster evaluation speed. And the pair chemistry team, and also in other like research groups, we have been developing these kind of machine learning potentials that is applicable for like different kinds of chemical systems. And there's a model called universal model for atoms called UMA, which is trained on different quantum mechanical calculations spanning molecules, materials, and analysis molecular crystals and like porous materials that kind of uses task embedding for different types of chemistry. And could be used universally over like all these kind of chemistry applications that given the input structure, this model will produce uh, the energy that is quite accurate when we compare to the baseline quantum calculations. So now we combine this kind of machine learning potential energy evaluation with the diffusion sampler to resolve this reactive energy landscape. And I'll skip like the detailed results, but even for these kind of like very challenging type of reaction where we have one transition region that links to two different uh, outcomes, we can leverage the bonding changes and translate that into the identified collective variables and apply well-tempered ASPS like sampling to explore the reactive energy landscape and resolve transition regions as well as the metastable regions. And we can see that the free energy barrier that we get from well-tempered ASPS is accurate with respect to what we can get with a well-tempered metadynamic simulation. So, but we can get this result in much faster walk clock time because we like well-tempered ASPS, the diffusion samplers can explore different directions at once. So it requires fewer energy evaluations. And one bonus is our energy function is also a machine learning model. So when we use like graph neural network for everything, then we can uh, batch evaluate the control model as well as the energy function. So it gives extra speed bonus. And in this case, we can also see this kind of procedure as effectively distilling a lighter sampler or control model from the heavier machine learning potential. Because when we train this model to be universal over like all different kinds of chemistry, then these models usually have like many or like large number of parameters and it's slower to run inference on. But diffusion sampler for specific chemistry can be much lighter. So during sampling, we're essentially distilling from the heavier energy model into the lighter sampler model. So that was like basic applications of well-tempered ASPS sampler. And finally, I will conclude this talk with future directions and remaining challenges. One caveat of this kind of sampling scheme, well-tempered in a sampling scheme, is that we need collective variables. And for some cases, like that I've shown before, collective variables are easy to identify. But for like protein folding and complicated chemistries, collective variables might not be easy to identify. So one example is combining it with machine learning identified collective variables. When we have like the unbiased molecular dynamic simulation at two different metastable states, then we can train some kind of classifier between two different states. And the classifier value will correspond to collective variable that distinguishes between two different modes of a system. And because of that, we can also combine this collective variable with well-tempered ASPS as well. And we can see that we also get a nice convergence behavior and good reproduction of the potential of mean force along the collective variable as well. So this is one way to alleviate the challenges of unknown collective variables. And this kind of well-tempered mechanism can also be combined with discrete samplers as well. So in this case, we explored the copper gold alloy system, which is essentially we have discrete lattice site, and we want to sample whether each lattice site corresponds to copper or gold atom. And we're given the energy function and we want to identify which kind of like configurations are possible and which configuration is more stable. And uh, in these kind of discrete settings as well, we get the mode collapse behavior at low temperatures. So for example, like at certain temperature, we should get like both copper 3 gold phase and copper gold phase, but like just using MCMC or like basic discrete sampler, we mode collapse into one like one mode. But combining this discrete sampler with well-tempered mechanism can uh, enhance the exploration of modes so that we can reproduce both modes correctly. Mm, yeah, so when we go to limitations, the most prominent one, in my opinion, is when we construct the bias for a specific system, then that bias is specific to that system, but we can't use that bias to enhance sample over different chemistry. So we lose kind of amortization, which is crucial for applicability of these diffusion samplers. One way forward is that we can get transferable collective variables. Like in theory, we have methods for constructing collective variables. And also the target bias, the same well-tempered bias that we get has a variational formalism, which means that we can parameterize it by a neural network and condition it on the input chemistry so that we learn this bias transferably over different chemistries. So there is still some hope, but there's like a major limitation of this approach. And secondly, is kind of like a broader limitation. But training with energy has been much harder than training from data. So training diffusion samplers like energy has to always compete with just generating data from existing molecular simulation and training a diffusion model from database approaches. So I think it's partially because molecular simulation has been there for a while, so we know all the hyperparameters, and that is efficient for sampling and all the tips and tricks for uh, the data generation. But we still haven't figured out how to consistently train a scalable neural sampler in chemistry yet. So that's also a major bottleneck if we want to apply this to actual chemistry applications. Maybe for the future works, I think one of the important feature is when we want to scale this approach or like in general diffusion sampler to larger constructs like protein that is solvated in water, then there's a challenge that the conformational changes in protein is usually slow and is sufficiently slow that building an IID sampler for that system is meaningful. But usually this protein is solvated in water and the movement of water molecule is pretty fast. So there's actually no separated, like usually unless the water is bound in a very specific position, the water is like there's no well-defined modes for water. And water sampling could be easily done with time correlated samplers like molecular dynamics as well. So we have separated time scales for different part of the system. And uh, yeah, we have to separate this kind of global versus local sampling and think whether like uh, which kind of sampler is required for the current system, or if there's like a way to coarse grain unimportant part of the system in the sampler setting. And yeah, there are a few other directions like multi-fidelity approach where we can train sampler with cheaper energy model and reweight with hopefully one later. And for solid system, I think if we really want crystalline minima, then we can also restrict the sampling by the symmetry group that the crystal have. And yeah, these are like the possible future works that I can imagine. Yeah, so this is end of my talk, and yeah, these are my collaborators, and thank you everyone for listening.
Yeah, thank you very much, Juno. Is anyone have any questions? Feel free to raise your hand.
Yes, I have some questions. Yeah, very nice work, and you combine a lot of different things like generative modeling, energy-based, and enhanced sampling together. So I have several questions, but I will start with some more general one. So for now, what's the dimensionality limitations? Is it almost the same as Boltzmann generators, or you can scale to larger system? Assume you have a expressive model and also a lot of data. Oh, yeah, very accurate energy function.
I think that's a really good question. And for methods like ASBS, the same sampler can be either mm, trained by data by using bridge matching, or trained from energy function by using the adjoint matching loss. And so basically, when we think of like system size, scalability, it because it could also be trained by data. And there's like a diffusion model for very large protein systems like BioEmu. I think the model capacity is sufficient to capture that larger constructs. But there's one challenge that I mentioned later where if we want to train something by energy function, then the energy is kind of feature of the entire system containing the protein and all the water molecule as well. So if we do this by database training, then we can just select the protein part and train a diffusion model for that. But if we want to do this by energy-based training, then we might also need to generate all these water molecules, which would be much more expensive because they're much more water molecule in a simulation box than a protein. So I think one enticing way here is training a coarse grain potential that, or like implicit solvent mole for proteins so that we can just sample proteins as well. And yeah, I tried that for signaling, and the caveat was that the distribution and, well, we are not thinking of kinetics here, but like thermodynamic and kinetic behavior of like proteins could be very different in explicit solvent and implicit solvent. So yeah, aside that, I think yeah, diffusion samplers uh, are promising for like scaling up to larger systems as well.
Yeah, yeah, okay. So here for all the energy evaluation, you use this UMA model, right? So I think it's again implicit solvent in this case.
So for previous to like alanine peptide benchmarks are done by Amber force fields, which is classical force fields. And for reactive sampling, I use the UMA model.
Okay, yeah. Yeah, also for the character variable discovery, you try this machine learning for character variable. What's the paper from Parinello again? What is it called?
It's the DTDA paper, the targeted discriminant analysis. So
Okay.
yeah, basically we have like two different uh, groups of samples from two different modes, and we project that to the input descriptor space, uh, like pairwise distances between selected atoms, and we train a shallow neural network that is trained to match one distribution to one Gaussian in the CB space and another distribution to another Gaussian, and yeah, and then train this like shallow neural network, like use the shallow neural network that is trained by this procedure as a cognitive variable.
Okay. Do you think this works well for alanine dipeptide from your experiment?
Yes, so for alanine dipeptide, ep is like a toy benchmark. So after a few iterations, usually methods all work for alanine dipeptide.
Okay. Then, okay, but for like larger system, have you tried like signaling?
I haven't tried signaling for like using this approach yet.
Okay. Yeah, I know there are a bunch of character variable discovery paper out there, but I don't know which one is the best. Do you have any
Mm.
recommendation?
I think it depends on like which type of yeah, which kind of workflow that we're thinking of. So there like the TDA is used when we have like samples from two different modes. But if we have some kind of like short MD simulation with time information, then we can use DeepTK, which is
Yeah.
also trained to identify flow modes. And if we have some like transition samples, then we can add that as an additional Gaussian as a transition state ensemble. And yeah, that's kind of different approaches. But I think deep TDA was pretty robust, at least for like toy benchmark systems. Yeah,
Yeah, okay. Okay, thanks.
Can I
thank you.
ask a question following this?
Mhm.
Um, you mentioned that you find the CV by using the data from both mode, but I mean, isn't this like a chicken and egg problem? You first need data from both mode, then you use it to define the CV space to sample from both mode.
That's a very good question. And I think there's like eventual challenge in CV discovery, like
Okay.
chicken and egg problem. So one like situation that this kind of workflow can be useful is when we know like single configuration from both mode, but like when we don't know where's like the transition region. So
Mm,
if we want to identify the transition region with the like sampling approaches, then I think it usually starting from collective variable discovery can be a good idea.
I see. Yeah, thank you.
Thanks.
Okay. So if there's no more questions, I think we just end here. Yeah. Thank you, Juno, for coming today, and thanks everyone for joining.
Thanks everyone for joining, and